Hello, everyone. Today I'm going to present my most recent work, Can MLMs Perform Text-to-Image in Context Learning? And this is a work under the supervision of my advisor, Professor Kangwook Lee, and a joint work with my brilliant collaborators, Yuchen, and Professor Cole. So I will start with introducing what is the InContext Learning, even though I know that it is already very familiar to most of you guys. So for large language models, it will take an input prompt and then it will know how to complete the sequence or answer the questions. So for InContext Learning, it is just a model adaptation method by just include some examples that demonstrates the downstream task objective. So here in the input prompt, we have two demonstrations. So we provide some examples of English to French translation, and just by providing those in-context demonstrations, the LLMs can adapt to the specified downstream task without the need for gradient updates for additional training. And in-context learning is also employed in computer vision, not just text context. So we can also use a vision model to perform visual ICL, where both inputs and outputs are images. So here we also provide the demonstrations of the segmentation, and now give a new query, and we can use a visual model to just perform this downstream task. So in addition to just handling those unimodal inputs, and now recently there are a lot of multimodal large language models has been developed. So multimodal large language models, they are capable for processing multimodal inputs, typically comprising both images and text. And one of the most famous MLM is Gemini. So in this example, we have a text plus image prompt. So we give some images and then ask Gemini what is this person is doing, and the Gemini can get the correct answer. And there are also many other famous MLMs such as Lava and GPT-4b. So the way how MLMs to process multimodal inputs is very easy. So for images, they usually just use a additional visual encoder to encode the images into some visual tokens, and we just concatenate them with those text tokens. So we can concatenate together and use them as the input of the LM. And many popular MLMs are using this structure like Lava and Qwen. And after the development of the MLMs, several efforts has been made to extend ICL to a multimodal context. So in this example, which is from the first image to text InContext Learning paper, so they here in their example, they provide the image, and the task is to provide the image caption, which describes what is the animal in the image and where are they mostly found. So now, give a new image of flamingo. If the MLM is able to perform this kind of in-context learning, it will generate an output such as, this is a flamingo. They are found in the Caribbean and South America. And actually, a recent advance of MLMs make those certain MLMs even can possess the capabilities beyond just processing the multimodal inputs. They can also generate multimodal outputs. This is just adding a visual decoder to decode those generated image visual tokens or beacons. And this structure is be used in those MLMs that are able to generate images such as Seed Llama. and EMU. And here is an example of like how this kind of MLM like handle both multimodal inputs and generate multimodal outputs. So in this conversation, the user just provide the seed lemma. So this lemma model is from the Tencent company, which is from the 2023 October. So in this example, in this conversation, the user provides a photo of Golden Gate Bridge and a photo of his dog. And the request is to generate an image of this dog sitting in front of the Golden Gate Bridge. And we found that the seed lemma is able to kind of combine the two images and even achieve more like customized modification to the image, like make the dog wear sunglasses or turn this image into an oil painting. So with this additional capability of generating multimodal outputs, so instead of considering just image to text in context learning, so we are here wondering whether it is possible to do the reverse, that is to consider the text to image in context learning. So why do we want to perform text to image in context learning, which we call T2I ICL here? So the T2I ICL here, we define it as like map. The task is to just learn the map of mapping the low dimensional texture data into high dimensional image data. So compared to image to text in context learning, this task would be more challenging, and it will also present its unique characteristics and will have distinct interesting applications. So here is an example of using the T2I ICL for interior decor design. So there are two demonstrations. So we just provide like texture instruction, study room, and then we provide a design, current design, decoration design of the study room. And we also do the same thing for the living room. And now we want an image for the bedroom, which should be in the same style. So given this query, actually this example is done by using the GPT-4V and DALL-E 3. And we found that it is able to generate a bedroom of the same style. And it can also be used for product conceptualization. Like provide iPhone and iPad, and if you want to design a car, so it will generate a kind of a car that in a style that Apple companies usually do. And we can also use T2I ICL for anime character design. So the first contribution of this paper is that we identify an important problem, T2I ICL. Since this is the first, this paper first kind of identify this problem, so the key question we want to answer here is, can MLMs perform T2I ICL? However, to answer this, we need to know how to evaluate the performance. So to do this, we introduced a COPSET, the first T2I ICL benchmark dataset. So let's rephrase the key question, can MLMs perform T2I ICL? So actually the main goal here, we just want to understand whether the MLM is able to learn the mapping between each text-image pair from the InContext demonstrations. So to study this problem, we here just present a example prompts from the dataset we designed. So here we have color as the textual instruction, and then an image of a car of the corresponding color as the corresponding output. So we have two demonstrations, and in this example, we have a latent information, which is a car, which is not provided in the texture instruction. We design the prompt like this because now the latent information can only be learned via InContext demonstrations. So using this way, we can really kind of try to evaluate whether the MLLMs indeed learn from the InContext demonstrations. So imagine if we directly provide both like the exact information, like the red car. If we directly use the red car as query of then even without the InContext demonstrations, the MLLMs still probability can generate an image of red car, right? And it has nothing to do with InContext demonstrations. So since our goal is that whether to know that whether MLLMs can learn the relationship between the text to image from the InContext demonstrations, so we just intentionally hide the latent information in the demonstrations only. And the expected output should be an image of a red car. So we have a lot of similar prompts with different objects like cup or chair, etc. And we also have many different colors. So in this first task, color I, we just have different objects as the latent variable for each prompt. And we also have different like texture instructions. And we also similarly collect the prompts for another thing, which is background. So in this themed task, so the textual instruction is also the attribute, which is like the background, the beach, desert, and glacier. And in the first example here, the model should be able to identify like that the goal is to generate a pig walking on the specified background. So for the first example, the expected output should be a pig in a glacier, in front, like on the glacier. And similarly, we also designed collected other themed tasks like style, action, and texture. So in total, in our benchmark, we have 5 different themes: color, background, style, action, and texture. And combine all of them together, it is the reason why we call our benchmark cup set. And for all 5 like tasks I just described before, we call them object inference tasks because we let the object to be the latent variable hidden in those InContext demonstrations. So the model needs to learn how to infer the objects from the demonstrations. But actually, we can do the reverse, like we directly provide the object as the texture instruction and use the attribute like color or style, use them as the latent variable. Then the task of the MLM becomes like infer the attributes from the demonstrations. So with these 2 types of tasks, object inference tasks, attribute inference tasks, each with 5 different themed tasks. So in total, we have 10 tasks. And for this dataset, we have collected 500 images collected from web or generated using GPT-4b. Using the DALL-E 3. And for each fixed number of shots, we designed 10,000 prompts. So now I have introduced the motivation and the COPSET benchmark dataset we have collected. Now we will use this dataset to benchmark the existing sorted MLMs in T2I ICL. So how to evaluate the performance of MLMs in T2I ICL? Here, I first just introduce the evaluation pipeline. So let's think about just take a random example from our COPSET dataset. So in this prompt, clearly the task is to generate a chair of a specific color. So in this example, the expected image should be a black chair. So assume that we want to evaluate one MLM, say MLM A, then we just feed the prompt into the MLM A. and let the MLM to generate an image. For example, like if it generates a black chair, then we want to know whether it is correct or not. So we just employ the lava as our evaluation model, because so lava is a very popular and widely used state-of-the-art model developed by the Yuchen Lee's group from our university, and it is has impressive performance, especially for the visual question answering. So we use this for like identify the color and objects or other attributes in the images. And actually, we carefully designed our dataset such that lava can identify the attribute and objects of all the images in our dataset correctly. So which means that like our dataset is in a suitable difficulty level such that lava can kind of evaluate the images correctly, and which also confirms that the reliability of lava in the evaluation pipeline. So here we just use lava to identify the attribute and object, and we found that the color is black and chair. So we just compare the output labels with the true label, and we found and then we find that they all match. So we just classify this generated output image as correct. So we just use this way to evaluate to calculate the accuracy of each MLMs on our dataset. And here I just quickly provide another example, like MLMB. Assume that it generates a wrong image, like a picture. So we just use the same, do the same thing, like ask the color and the object from the lava, and lava just compare the lava's output with the true label. And here, because pink doesn't match with black, so we just classify this generated output as wrong. So actually, we know that like there are some MLMs are able to generate images such as EMU, GIL, and Seed Llama. But actually, there are many more famous MLMs that do not possess this capability, such as Lava, QVL, and GPT-4v. We know that if we use ChatGPT, it can like generate images, but it's not GPT-4v. So what they're doing is like they are calling the diffusion model, the DALL-E 3, in their their user interface. So GPT-4v itself cannot generate any image. So because our goal is to see whether they are able to, like, one of the goal of like our projects to evaluate whether those models are able to learn the mapping from the text to image from the in-context demonstrations. So we just want to see whether those those models are able to learn from the demonstrations, especially in this T2I scenario. So what we can do is actually if they cannot generate image, we can directly just add one more sentence to instruct them to generate the description of the image. So we still provide the same prompt, but at the beginning of the prompt, we can add some sentence to instruct the model to generate the description instead, such as, I will provide you with a few examples with text and images. Complete the examples with the description of the next image. So so in this case, we can just check their output. Like, for example, if it's like black chair on white background, we can still use lava to identify whether it is correct or not. So the evaluation is basically the same as the image generation mode. So in our experiment, we considered two modes. And now we visualized the generated output from the three models that are able to generate images. So here are the examples from the color eye task. So we found that Seed Llama seems to work very well. And actually the Seed Llama has generated the correct image for all 6 examples shown here. Like for the first one, it generated a purple backpack. In the second example, it generated an orange car, etc. Oh yeah, and here are some example outputs from the background eye task. And we found that EMU actually couldn't perform T2I ICL very well because it always generates some random images with the road. Yeah. And GIL sometimes sometimes works, but sometimes not. And here we just visualize the exact accuracy we calculated for those models. So we have conducted the experiments on 4 different settings. The first is 2 shot, and 4 shot, 6 shot, and 8 shots. So by just observing the results from the 10 tasks, we found that in general, T2I ICL is a challenging task. And all evaluated MLLMs failed to achieve satisfying results on most of the tasks. But still, among them, we found that the C-lemma achieved relatively good performance on some tasks, like especially the color eye, background eye, color eye, etc. And here is the results for image description generation mode. So we just add one more sentence to instruct the models to generate the image descriptions. And what we found is that in this case, GPT-4V and Qwen VL works very well, and all the other MLMs failed to achieve satisfying results. And one notable observation I want to mention here is just the accuracy doesn't increase with the if we increase the number of demonstrations. So for example, if you look at the result in the color eye, and we found the GPT-4V performance actually keep decreasing as we increase the number of demonstrations. So the reason for this, there are many reasons for this. So the first one is actually in the natural text or in the natural internet content, most of the time it's very unlikely to have one prompt that have more than 8 images, right? Especially like for lava, I think most of the it's most of training on some prompt that only contains 1 image. So with more demonstrations, maybe it's very rarely seen in the training data set, so the GPT-4V's performance keep decreasing. But still, there are for Qwen VL, if we increase the demonstrations from 2 to 4, the performance increased. Yeah, so there are many factors contribute to this problem. Probably in the future, if we have models that train on more images, train on a prompt with more images, probably the performance would be different. The phenomena would be different. Okay, so now I just want to show you a closer look of the results of those models on performing the T2I ICL. So here are 2 examples from the color eye task. So first observation is that we found that lava, instead of performing T2I ICL, it always describes the images in the prompts. So if you look at the example in the left-hand side, the lava's output is the next image should be a close-up of a blue backpack with a brown strip. So actually it is just describing the last image presented in the prompt instead of making any prediction. And if you look at the example in the right-hand side, the lava's output is the next image should be a close-up of the in front of purple sports car. So actually it's also just describing the last image in the prompt instead of making any prediction. So this could be attributed to the lava is mostly trained for visual question answering instead of interleaved text and images. So this could be the reason. And Gil, we found that Gil failed to generate coherent sentences. And Silema, the bad performance is because that it always generates images. So if you see their response is like, I have generated image. So we cannot force it to just generate, like I have tried multiple ways to prompt the Silema to try to prompt the Silema to generate image description instead, but none of them works. And lastly, we found that GPT-4V and QVL works very well. If you take a look at the, maybe right-hand side example, the QVL just say the next image should be an orange sports car, and the GPT-4V's answer is a sleek race car in bright orange, which means that like both the GPT-4V and QVL, they understand, learned things from the InContext demonstrations and can make the correct prediction. Oh, and another thing I want to mention is that like before I described that we use Lava as our evaluation model, but here we find that Lava's performance is not good, but actually does not conflict with each other, because in our evaluation pipeline, we only use Lava's visual question answering ability instead of InContext learning ability. So even Lava's InContext learning ability is not good, it is sufficient for it to be a good evaluation model, and we have already confirmed its accuracy in identifying the attribute and objects of the images. Okay, so now just based on the experiment results I just shared previously, and for the two mode, image generation and image description generation, we identify the best models. So for image generation, of course, the C-lemma is the best. And for the image description generation, we found that both QVL and GPT-4V works very well. And because of so in the following experiments, we just choose to use those top performing models directly. But because the GPT-4V is not free, so we in the following all experiments, they are either conducted on the C-lemma or QVL. So now we have already shared the experiment results of those MLMs in T2I ICL, and we found that actually lots of like many MLMs, they are struggling to achieve very satisfying results in this task. So now we want to explore more to understand the challenges in T2I ICL tasks. So why T2I ICL is challenging? We have two hypotheses. First, it is due to the intrinsic complexity involved in processing multimodal data. So we know that for standard InContext learning, like in the context of text, like for just large language models, not multimodal large language models, they can, like InContext learning can improve the performance a lot. And there are a huge amount of evidence to support this claim. But we found that in this multimodal context, it is not the case. So the first hypothesis is just like whether maybe it's just processing the multimodal data itself is make it harder. And the second, it could also due to the inherent difficulties associated with the task of image generation. So for instance, let's think about some image or some query we have in the composite dataset, such as like a pig walking in the glacier, right? But actually, in reality, it's very hard to find any true images like really have a pig walking in the glacier. So it's very unlikely for those training set of those MLMs to have such kind of images. So maybe this kind of long tail or out of distribution make the model itself too hard just generate in terms even generate the image. Like even if we directly ask it to generate the pig walking in the glacier, it might be also challenging. So this might not just only because of understanding the context. So to verify the first hypothesis, is multimodality a primary challenge in T2I ICL? So we conduct an experiment to compare the T2I ICL versus texture ICL. So this is the default prompt that form of prompt we used in our data set. So here we provide two demonstrations and we hide the latent information, which is the car in the demonstrations only. But now we replace all the images in the prompt with its corresponding description. So in this case, now the prompt becomes a completely just text. There's no images at all. And we want to see whether the model is able to generate the correct description of image or just correct image. And indeed, we find that TICL, the textual ICL, significantly outperforms T2I ICL, especially if you look at the 4-shot case for the seed llama, we found that TICL outperforms the T2I ICL on 9 out of 10 tasks. And for the QVL, for the 4-shot case, the TICL outperforms the T2I ICL on all 10 tasks. So this kind of verify our hypothesis, which means that the multimodality is the primary challenge in T2I ICL. And now, next, we want to verify the second hypothesis, which is the image generation a primary challenge in T2I ICL? So now we just directly provide the explicit texture instruction and see whether the model is able to generate the image or not. So we performed the experiments on seed llama and we found we observed that employing the precise texture inputs indeed improves the performance. However, even if we employ precise texture inputs, the accuracy are still not satisfying. So if you look at the 4-shot case for the objective inference task action I, even with the precise texture inputs, the accuracy is still as low as 0.161. So which means it still cannot just directly generate the correct image, even if we tell the model what kind of image we want to generate. Now, so after understand the challenges which make the T2I ICL hard, next we are trying to improve the MLLM's T2I ICL capability. So we tried some possible solutions on a very small scale experiments. So the first is fine-tuning MLMs on copset. So there is a well-known paper for large language models called Meta-ICL. So for the Meta-ICL paper, they found that if we train a model, a large language model on some InContext Learning data sets, then its general InContext Learning capability of the model will be improved. So we just want to verify whether this approach can also be adapted to the multimodal context. So to study this, we split our data set into a training set and a testing set so that the fine-tuned model will be tested on unseen queries. So here is the experiment results on the QVL. And we find that the performance of T2I ICL is significantly improved after we fine-tuned the model. So this means that fine-tuning MLMs on T2I ICL datasets enhances the general T2I ICL capability of MLMs. And another thing we tried is train of thought. So train of thought is a very popular prompt engineering technique for large language models, right? And it has shown very good, impressive, empirical results on many tasks. But here I just want to give you a more like introduction about what is stream of thought and how we integrate it with the T2I-SL. So in our experiment, we just like here provide the prompt, and after that we add one more sentence. Before predicting the next image, let's first think step by step and analyze the relationship between the text input and image output in each example. So for this kind of prompt, we just make the model to generate the reasoning first before making the prediction. So it will generate a train of thought. And here is the response from the seed lemma. We can just look at the last sentence. So it just says, from those examples, we can see that the text input is related to the color of the leaf in the image output. The input color is used to describe the color of the leaf in the output images. And then after receiving the analysis, we just ask the model to describe what the next image should look like based on the analysis. And the seed lemma will generate the image for us, correct image for us. So here we found that after integrating the stream of thought, it greatly improves the performance. This is mostly like observed in the for-sure case for seed lemma. However, for QVL, it was not the case. So for QVL, we found that even after like using the stream of thought, the performance seems not like always consistently improved. So we just take a closer look to what happened for QVL. So we just found that the suboptimal performance of COT plus T2I-SL on QVL can be attributed to the instance where the QVL might like fail to answer the question or fail to execute, like follow our textual instruction. For example, here it just say, sure, I will do my best to analyze the relationship, but you need to provide examples, and then just say, sorry, it doesn't have any examples to analyze, etc. So there are many these kind of cases. So we have tried to like prompt it to perform the COT better, but we didn't succeed, and it is kind of beyond of the current scope of our paper. So anyway, the conclusion here is that while COT shows promising results on certain MLMs, a more detailed examination is needed for COT to achieve consistent improvements across different MLMs. And we also tried another prompt engineering, where it is just like provide a more clear task description. So of course, when we designed the data set, we indeed try to hide some information to make to better evaluate the model's ability of like learning from the in-context demonstrations. But here, because we just want to know how does the prompt engineering techniques affect the results, so here we just also like provide additional instruction, like please identify the common main object in the images and generate another image of this object in the requested color. So with this more clear or explicit instruction, we found that the performance is also improved a lot. So now we have introduced, we identified the T2I-SL, this problem, and we introduced the COPSET benchmark and share some experiment results. Now I want to wrap up today's presentation by summarize what I just presented today and share with you about the limitations and possible future works. So first, in this paper, the first contribution is that we identified an important problem that has not been systematically studied before, which is text-to-image in-context learning. And we introduced the first dataset for benchmarking MLM's T2I performance. And with this dataset, we benchmarked MLMs and found that many MLMs struggled to perform T2I ICL effectively. Fourth, the main challenges in T2I ICL stem from understanding the multimodal information, and second, the complexity of image generation. And lastly, we also explored some techniques for improve the MLM's capability in terms of performing T2I ICL, such as fine-tuning. We found that fine-tuning works well, and we also tried some prompt engineering techniques. They use promising results on some MLMs, but requires further investigation for consistent gains, because for some MLMs, they might refuse or cannot work as what we expected. So lastly, our paper, because it is the first work that tried to benchmark the MLM's capability in terms of the T2I SL, there are many limitations and opens a lot of very interesting questions. So here I just list 4. First, we know that the demonstration selection can have a huge impact in the performance in context learning. And this has been well studied in the context of large language models, but it is not, we're not sure about multimodal large language models and for this mode of context learning. So one possible question is to what extent does the input image quality affect the generated image's quality? So we're not sure. Probably even with low quality image in the prompt, as long as the model understands the relationship between the text and image, probably it can is able to generate some high quality image. And second, we have tried some prompt engineering techniques such as train of thought, etc. But we just perform a very small scale experiments. But actually, probably there are many more things that we can do. For example, we can do more careful prompt engineering, such that at least for Q1, it can maybe execute the COT successfully. And we can also try many other very interesting, well-known prompt engineering techniques such as self-consistency or tree of thought, etc. And third, I believe that most of you have noticed that in the examples in our data sets, actually we only, and especially when we evaluate the generated images, we only care about whether they generate the correct attributes and object or not. Actually, we are not care the quality of the output. For example, sometimes probably we expect maybe first we expect if we have the 2 demonstrations, they are 2 chairs, identical chair, but just with different color. And now we have 2 new models. One is able to just generate an identical image of the identical image, but with an updated color. And another model, maybe it just generates some other shape of chair, but it is correct. It generates the correct color and the object is also correct. But probably we sometimes prefer an identical image, right? So, but now in our current design of the experiment, we don't care about the quality of the generated output. So, and this is because it's the first work, so we just want to evaluate the basic capability of those models on performing the T2I SL, whether it can understand the relationship between the text and image to a certain very basic level of extent. So if we want it to have perform a more complicated task like image editing, then we need to more carefully design the data set instead of now we have red car, blue car, but they are different cars just with different color. But so if we want to use the T2I SL for image editing, then we need to collect the images of the same chair but with different color, etc. So if we want to consider more challenging problems, we need to more carefully design the like evaluation and also the data set. And also, if we as I before I mentioned or shared with you 3 example applications, their interior decor design or product conceptualization. Of course, our current data set cannot like evaluate those MLMs capability in terms of those like very real advanced applications. And this is also because that the current MLMs, they still are not that advanced enough to perform that kind of like to work for that kind of applications. So, but in the future, as the models are like developing very fast and more and more advanced models are like released fastly. So in the future, if we want to kind of evaluate those models on more advanced tasks, then we need to explore a wider range of themes, not just like color or style. Probably we would have some more fine-grained themes like clothes, etc. And yeah. So this is the end of my today's presentation. And here is the QR code for the paper summary in Twitter and the GitHub repo. And thank you all for listening.